Hello, everyone. This is the fifth in a series of lectures covering chapter 35. Today, we'll be talking about Huygens principle and the dispersion of light. So, the Danish scientist, whose name is funny to pronounce, it kind of sounds like Huygens. Basically, he was a pioneer of the theory that light behaved as waves. So he came up with this model to model the waves, the propagation of waves through wavelets. So what he basically said was, at any point in time, if you're looking at a wavefront, you can construct the future shape of the wavefront as it keeps propagating by drawing this secondary waves called wavelets that propagate outwards from the wavefront. So you would basically treat every point in your current wave as a source of wavelets, and the wavelets again move at the same speed in the same direction of propagation, and then wherever you let the wavelets go to, whatever time you decide has passed, then you can find out the new position of the wavefront by drawing a surface tangent to the wavelets. So it's essentially this Huygens principle basically lets you construct wavefronts in different points in time by drawing wavelets based on the current wavefront. So, for example, here's two drawings of the application of the principle where in drawing A, you have a linear wavefront. So you just draw a few wavelets for clarity, which emerge from points in all the wavefront. And the wavefront here moving to the right. So you know the wavelets will also move to the right. And after some time has passed, the wavelets now are like points B and B prime. So to find what the new wavefront looks like, you just draw a line tangent to all the wavelets, which will get you a vertical line, which again makes sense that it has the same shape as the original wavefront, since all it's doing is moving to the right. For a spherical wavefront shown in B, you have the old wavefront, and at any point on it, using the principle, you treat it at any point, in this case just 4 points for clarity, as a source of wavelets. And then the wavelets, since from every point has a direction that's normal to the circle at that point, normal to the sphere, each wavelet then collectively propagate radially outwards. So the new wavefront will just be a bigger sphere. So in this case, right, it seems obvious what the new wavefront's going to be, but just looking at how the wave is moving or rippling out. But in cases of more complex wavefronts, Huygens principle gives you a good way to use the geometry of the wave to determine what it'll look like in the future. You can actually use this principle then to come up with the law of reflection and the law of refraction. I think I said reflection. I think I said refraction twice there. So to restate, the Huygens principle can be used to derive the law of reflection by talking about the wavelets propagating outwards from two different rays. And the principle can also be used to derive Snell's law. I leave the derivations in the textbook, though they're worth your time if you want to learn a bit more about wave geometry. It's a good exercise. So, next thing to talk about is dispersion. The idea is that for any given material, the index of refraction actually varies a bit depending on the wavelength of light. So white light, for example, is actually made up of a big range of wavelengths, which to the eye appear as different colors of a rainbow. So from the longer waves that make up red light to the shorter waves that make up purple light, there's a whole range of colors in between, that together will make up a beam of white light. So it turns out that materials tend to refract shorter waves than longer ones. So in a prism, violet light in the sort of lower end of the rainbow refracts more than red light does. And if you look at the graph here for different materials, you can kind of tell that as you go towards the right on the graph, towards longer wavelengths, towards from purple to red light, crossing entire spectrum of white light, the index of refraction for all these materials drops. And that means that with a lower index of refraction, if you're coming from air to these materials, the angle of refraction is going to be smaller as the light gets redder, as you go towards the right on the white light spectrum. So that's why in a prism, when white light enters a prism, it refracts twice, and this causes dispersion since the different components of white light are refracting as a function of their wavelength. They have different indices of refraction inside the prism. So the ray is going to come out on the other side as this sort of beam of multiple colors. Is kind of like a rainbow. Perhaps fans of Pink Floyd will have seen the famous light entering the prism and living as a rainbow. The album cover for The Dark Side of the Moon, though, gets it wrong, that in the middle it shows a white light, but in the middle of the prism, the dispersion has already occurred. So you also see a rainbow inside the prism, just not as fanned out as the one outside the prism, which is, at that point, it's a second refraction. So the dispersion effect is much more noticeable as it leaves the prism. Newton, besides doing a lot of work in gravitation and also British economics, did some work in optics, and he noted that he was able to measure, the fact that each color coming out of the prism had its own angle of deviation, so was able to suspect a relationship between the components of light and the index of refraction. And you can actually focus the light beam once again. You can focus the dispersed light, combine them again into white light. So next chapter, we'll actually talk about lenses that help you focus light with the right construction. So the rainbows we see after a rainy day are a cool example of dispersion, reflection, and refraction working together, because they result essentially from sunlight hitting against water droplets in the air. And if you can imagine water in the atmosphere, from rain or just a humid day, what's going to happen is that incoming rays of sunlight, starting off as basically white light, are going to hit these atmospheric water drops. And what will happen is the light, some of it will transmit into these drops of water, and it'll reflect back. And a lot of reflections can happen before the light beams actually get out of the water drops, but the most intense ones will come out after a single reflection of the back of the drop, and then they'll refract back into the air. As you can see here in the drawing, the most intense rays of light will come out, and they'll only do one reflection of the back and then reflect off towards the bottom left and refract back into the air. So these are the most intense rays of light, and there's a whole dispersion spread where essentially the drops act as a prism. In this drawing, you only really see the violet and red lights, but the whole rainbow is here. The whole spectrum of white light spread out between these two rays at the bottom. And since their refraction is a function of their wavelength, what ends up happening is that there's obviously a slight angular difference between the different colors of the white light that have now spread out. So there's a 40-degree angle between the most intense component of violet light and the incident sunlight, and there's a 42-degree angle between the red light and the violet light. So this angle, while small, is enough to generate the rainbow, because since suppose that there's a rain cloud, so there's raindrops throughout the sky. What will happen is that sunlight will hit all these raindrops, and it'll spread out the sunlight into different colors, and then it'll reflect the colors back into the ground. Because the most intense colored light falls to the ground at different angles, different parts of the sky will reflect different parts towards your eyes. The most intense colors that reflect into your eyes depends on the where the droplets are in the sky. So for droplets lower in the sky, they'll be able to reflect the most intense violet light towards you. The droplets a bit towards the middle of the sky will reflect the green light, the most intense green light towards you, and then the most intense red light would be reflected off towards you from the droplets higher in the sky. And at this point, though, if you look at the drawing, right, you have the upper part of the sky, you have sunlight coming in, the blue arrow at top, and it reflects into and reflects off the water drops, right? They're acting as a prism. You can see how the dispersion happens, but the violet lights and the yellow and the greens and the blues kind of pass over your head, and only the most intense red light has the right angle to reach you. But for a white beam of sunlight, shown below the one on top, this one, when it hits the droplets and they disperse light towards you, it's actually most intense violet light that hits your eye. The red one passes below your eye. So effectively, over some altitude, you're only receiving certain colors in your eye, and so that lets you see this rainbow shape. Interestingly, because reflection and refraction happens every time the light reaches an interface, the light that enters the raindrops, the most intense one, right, will only reflect off the back once and then come towards you, creating the first rainbow. But part of the light keeps reflecting inside the drops until they finally leave back into the air. So all the light beams that get to reflect twice on the raindrop and then reach you form a second rainbow that's actually upside down. It's inverted in colors. Now you can't see this, but third and fourth rainbows can also form because some of the light, a very small portion of the light, will still keep reflecting a few more times in the drops before leaving. But at that point, after enough reflections, the reflected light that gets refracted out after enough reflections will have lost most of its energy, so the consecutive rainbows look very faint. Though apparently in lab experiments, they've been able to create about 30 reflections with incident white light. But still, the intensity of each rainbow drops off after the first due to the loss of light due to refraction. There's some cool effects that happen. For example, there's the halo effect, which has its name in German in the chapter slide here. I will not attempt to pronounce it. But basically, it's an optical effect that happens in summer mornings where you're looking at the dew on the grass, and if you look behind and see your shadow, light's actually gonna kind of disperse around the crest of your shadow, and it'll hit the dew. They'll hit the dewdrops in the grass, and that'll cause some retroreflection. The light around the sun passing through your shadow will get reflected back at you, so it'll look like there's a halo around your shadow. But that's just, again, light from the sun reflecting off the dewdrops. The rainbows can also have this sort of like interference effects, as different parts of it have to travel different distances to reach you. So there's sort of like this constructive and destructive interference even for visible light. Sundogs are this kind of like halos, these rings that form around the sun. This happens in particularly cold days in the winter, where the frozen ice crystals in the atmosphere basically act as prisms that, well, they act more as lenses that kind of spread out the light from the sun in a very particular halo effect. Not all crystals necessarily will create a full halo. They'll might just create like a kind of like slight diffusion of the sun. But if the crystals are particularly long, then the refraction from the crystals, the sunlight will get refracted in such a way that it'll actually form a huge halo. Oh, so this is interesting. If you've ever been driving on the highway, sometimes it looks like there's like a small like puddle on the roads, quite a few cars ahead of you. But then when you approach the puddle, it disappears and it's just more road. So what's happening is that this is kind of tricky, but up the air right above the roads is warmed up by sunlight, and this kind of affects the roads, affects the air, and the hot air. What it'll do then is that light that's coming from the sky at a kind of like a shallow angle, kind of almost like parallel to the roadway, will get refracted. So what you'll end up having is light not being able to reach the roadway, and it's just reflecting off the sky. So what looks like a puddle is actually an image of the sky on the roadway. Quick quiz here. You want to pick a right lens for your camera. You want one that reduces the chromatic dispersion, which is just the fact that light's gonna fan out into its different color components as it passes your lens. So you wanna pick a lens made from a material that minimizes the amount of dispersion. If you look at crown glass, there seems to be a particularly strong correlation between the index of refraction and wavelength of light. You go from 1.53 to about 1.51 from red to purple. Same with acrylic, there's seems to be a big change. But if you look at fused quartz at the bottom, the index of refraction does go from like 1.47 to 1.46 for from blue to red light. Sorry, from violet to red light. But once you hit about the yellow light range, the index remains pretty stable. So that means that since there's just such a strong relationship between wavelength and index of refraction for fused quartz, it means that the amount of refraction, the amount of dispersion of light will be less than the other two materials. So you probably go with fused quartz. Now, professional camera people will actually combine lenses to further minimize effective dispersion and therefore get a really good image. Anyways, that's all for today's lecture. Join me next time where we'll talk about total internal reflection.